we're going to talk about some specific types of distributions. Namely, today we're going to talk about the binomial distribution and the multinomial distribution. So first off, we have to talk about how we're going to collect data. So for the binomial distribution, we're going to be using a process called the Bernoulli process. Now, an experiment is following the Bernoulli process. It does 4 things. So the first thing is it has to have repeated trials, right? So we've got our repeated trials, and then every trial has to be able to be categorized as a success or a failure. So that automatically tells us this process is pretty applicable in the world of engineering where we're thinking about defective or not defective parts. It's also very applicable in the world of, say, pharmaceuticals, where we're interested in whether a drug worked or not. Really, lots of different possible applications here. So we have our repeated trials. They can be categorized as successes or failures. Then we have to have some probability that we can assign to success for every single trial. So I can't say that the first trial has probability of success P and the second trial has probability of success R and just keep on changing the probabilities. They have to remain constant from one trial to the next. So I have multiple trials, success or failure for every trial, the same probability of success for every trial, and finally, those trials must be independent. So going back to thinking about drawing cards from a deck, if I draw the cards from the deck and I take them out and remove them, then the trials aren't independent. But if I replace the cards, then they are independent. And so those are our 4 things, right? Repeated trials, success or failure for each trial, the same probability of success, and those trials are independent. And if we've met all of those things, then we followed the Bernoulli process. So once we followed the Bernoulli process, the binomial distribution actually simplifies a lot of stuff that we've been talking about. So it's a fun distribution to work with. And the multinomial distribution, the only difference is it's going to allow us, instead of having only 2 possible outcomes, success or failure, we're allowed to have more than one possible outcome. However, it's going to follow all the rest of those rules. All right, so let's take a look at how the binomial distribution works and look at an example or 2, and then we'll look at the multinomial distribution and again look at an example. Let's consider this experiment where we're taking 3 trials, pulling objects and determining whether they're defective or non-defective. Now, we're going to consider it a success if we identify a defective item and it doesn't get out into the world. So we have 8 possible outcomes in these trials. I can go from all 3 being not defective up to all 3 being defective and any combination between. And I have a number of successes, my random variable x, for each of those possible outcomes, and those values range from 0 to 3. So I can make a probability distribution, f of x, of my random variable x, the way I have before. So x can take on the values 0, 1, 2, or 3 successes. If I want to find the probability that there are 0 successes, so I want to find f of 0, what I'm going to do is I'm finding the probability of all 3 being not defective. If there's a 25% chance that each is defective, then the probability that I find 1 not defective, and the probability that I find another not defective, and the probability that I find another not defective, well, each one of these is 3/4. And since these are independent trials, then I get to just multiply 3/4 times itself each time to find my probability. And when I do this, I get 27/64 as my probability. Now, if I want to find my probability distribution value when x is 1, I need to consider all the possible ways that I can have 1 as a value. So I'll have the probability that I have a non-defective, and then a defective. And since these can't occur all together, they're mutually exclusive, I can add to that the probability that I find non-defective, defective, non-defective, and the probability that I find defective, non-defective, non-defective. And I can find each of these by multiplying the way I did above. So probability of non-defective times the probability of non-defective times the probability of defective. And I can do the same thing for each one of those. So this is going to equal the probability of non-defective was 3/4, or 1 minus my 1/4. And the probability of defective was 1/4. So if I multiply this, I'll be doing this for each one of these, just in different orders, right? So if I multiply this, I end up with 9/64, and then the next one will also be 2 3/4 and a 1/4 multiplied together, giving me 9/64. And the third one will be the same, 9/64. And so I'll end up with a total of 27/64 as my probability of having 1 success, finding 1 defective. Now, if I follow a similar process for when x is 2, I'm going to end up with 3/4 times 1/4 times 1/4. So 3/64 added together 3 times, giving me a probability of 9/64. And then finally, taking a look at the probability of 3 successes, I'll have all 3 are defective, so 1/4 multiplied times itself 3 times, and there's only one way that happens, so that gives me a probability of 1/64. So here's my probability distribution. So the ways that we've been doing probability distributions 100% work in this case. The great thing for us is this actually follows that entire Bernoulli process where I have repeated trials for my experiment, and each of them is classified as either successful or not successful, and each one of them has the same probability of success for each trial, and the trials are all independent. So since I have that, then I can use the binomial random variables to help me out. So this is a binomial random variable, and it follows the binomial distribution. So binomial distribution tells me if I want to know what my probability distribution value is at x when I have n trials, each with p probability of success. This tells me that I can actually find this by taking my n trials, choosing the x of them that are going to be successes, and multiplying that times the probability of success raised to the power of my number of successes I'm looking for, times this value q, which is going to be my probability of not successful, times the number of not successful trials I have. So we're going to have q equals 1 minus p is the probability of not successful. Right, so let's take a look at what I have here and see if we can fill this in. So instead of having to have calculated this the way I did, let's say I wanted to know my probability of finding one success when I had 3 trials, each with probability of success 1/4. I'm going to be doing 3 choose 1 times my probability p 1/4 raised to the first power times my probability of not success 3/4 raised to the 3 minus 1 or 2 power. So I know that 3 choose 1 is equal to 3 factorial divided by 3 minus 1 factorial times 1 factorial. And I have 1/4 to the first power is 1, and 3/4 squared is going to be 9/16. This is going to equal 3 factorial divided by 2 factorial divided or times 1 factorial times 9/64. So this is going to equal 3 factorial divided by 2 factorial times 1 factorial. 1 factorial is just 1. So this is 3 factorial divided by 2 factorial, which is just 3 times 9/64, which will give me my 27/64. So notice that it came to this 27/64. And I didn't have to go through thinking all of the possible ways that I could get 1. Instead, I got to just calculate them all in one go. And I can do this for every single one of my x values along the way. So if I was asked for the binomial distribution of this random variable, what I would do is I would leave the x as an x, and I would fill in the n and the p. So my n of 3 and my p of 1/4. And I would be able to write this as 3 choose x times 1/4 to the x times my q value I can calculate because I have p, so 3/4 to the 3 minus x. And I would be able to give this, and I would be able to know that x can go anywhere from 0 to n. So x is going to equal 0, 1, 2, or 3. So what we've essentially done here is we've given ourselves a way when we're in this binomial random variable situation, we have a binomial distribution, that I can actually give you an equation for the probability distribution instead of having to give a table like we've needed to before. So here we have an example. We have the probability that a patient recovers from a rare blood disease is 0.4. If 15 people are known to have contracted this disease, what is the probability that from 3 to 8 of them survive? So the first thing we need to do is pull out the information that we have. So we're going to say that recovery is success, and there's a 0.4 chance of it. So P is going to be 0.4. Then we also need to figure out what our n value is. So n is going to be the total number of people that we have, the total number of trials. So here we have 15 people. So that's our n. And then we need to look at what values of x are we interested in. Then we need to think about what values of x are we interested in. So we have from 3 to 8. So we want 3 is less than or equal to x is less than or equal to 8. So what this means is I need to add my probability distributions. So I'm going to actually have the sum from x equals 3 to 8 of my probability distribution value at x, and I plug in my n of 15 and my p of 0.4. Now, I could write this out and have a value for 3, 4, 5, 6, 7, and 8, but that's a lot. That's 6 different ones of these binomial coefficient things that I need to find to add together to find my probability. Now, there is an easier way to do this, and it makes use of a table that's found in the appendix of your book. So this table is table A1, and it's found in the printed book on page 726. So it's the first thing in the appendix. And what this is it gives you the binomial probability sums starting at 0. So you have the sum x equals 0 to r for our binomial distribution of r in p. So what we want to do with this is we want to be able to make use of this table. So what we can do is we can look and we can say, well, we want to go up to 8 as our starting. So let's say we take the sum from x equals 0 to 8 of our binomial coefficients, x with 15 as our n and 0.4 as our p. Well, if I do that, then I've counted 0, 1, and 2, and I didn't want to. So I need to subtract out those 0, 1, 2. So I need to subtract out the sum from x equals 0 up to 2 of the same binomial coefficients. I've got x, I've got 15, and 0.4 as my p-value. So now I can use the table. So I'm looking for when n is 15 as a start. So I find that on page 729. I find that if I have a sum from 0 up to 8, I find r is 8 for my row, and I work across to 0.4, I find that that binomial probability is 0.9050. And then I subtract from that, I still need n equals 15. This time r, my top value is 2, so I'm going to go to that row and then over to the 0.4 column to find that I have a probability of 0.0271. So now all that's left for me to do is this subtraction, and when I do, I find that I have 0.8779 as my probability. So this equals my sum from x equals 3 to 8 of my binomial probability distribution values, when 15 was my n and 0.4 was my p. So that means that there is an 87.79% chance probability that 3 to 8 of the patients survive. Now, perhaps the happiest news of all of this is we've had these complicated formulas to find the mean and variance of our probability distributions. Now, when we're dealing with a binomial distribution, the mean is simply the n value times the p-value. And the variance is simply n times p times q. Now, when we talk about the multinomial distribution, we have a setup where we again have multiple trials in our experiment. And a given trial can result in any one of k possible outcomes. We'll call them e sub 1 up to e sub k. And each one of those possible outcomes has a corresponding probability for it. So e sub 1 happens with a probability of p sub 1, and e sub k happens with a probability of p sub k. Then our multinomial distribution, what it does is gives the probability that e sub 1 occurs x sub 1 times, e sub 2 occurs x sub 2 times, and all the way up to e sub k occurring x sub k times in independent trials. And of course, our x sub 1 up to x sub k are going to sum up to n because it has to take on any one of our k outcomes. And p sub 1 up to p sub k is going to sum up to 1 because, again, we're accounting for all of the possible outcomes, and so our probabilities have to sum to 1. So we write this as f of our list of x sub 1 to x sub k with a semicolon separating that from p sub 1 up to p sub k, and then at the end we put an n just for us to be able to double count or double check that we have everything accounted for. Now, the n also helps us out when we're calculating this. It's equal to n choose x sub 1, x sub 2, all the way up to x sub k. And then we multiply that times the probability of event 1 occurring to the x sub 1 times the probability of event 2 to the x sub 2 times, and so on up to the probability of event k to the x sub k times. Now, just a quick note, because we haven't actually looked at n choose x sub 1, x sub 2 up to x sub k before. The way we calculate this is we do n factorial divided by x sub 1 factorial, x sub 2 factorial, and so on, all the way up to x sub k factorial. And we can do this because x sub 1 up to x sub k added together is equal to n. So let's take a look at an example of this. So here we have the setup of an airport with 3 runways. And we're looking at randomly arriving commercial jets, where the probability that they use runway 1 is 2/9, the probability that they use runway 2 is 1/6, and the probability that they use runway 3 is 11/18. Now we can check that these probabilities add to 1, and they do. And then what we want to know is the probability that 6 randomly arriving commercial jets are distributed in this fashion. So we have 2 going to runway 1. Well, since this is the probabilities that we're looking for, this is x sub 1. And then runway 2, having 1 go there, that's x sub 2. And having 3 go to runway 3 is x sub 3. So I can use the multinomial distribution. So I'll have f, remember I had x1 up to xn, so I'll have x1, x2, and x3. And then I put a semicolon and I put my probabilities, so probability 1, probability 2, and probability 3. And then finally, I put my n value. So I can plug these things in. So this is going to be, for me, x1 is 2, x2 is 1, x3 is 3, probability 1 was 2/9, probability 2 is 1/6, probability 3 is 11/18, and n is my total number of planes, so I add up my x1 to x3, and I have 6. So now I can follow a formula. So that was n, choose x1, x2, x3, times probability 1 to the x1, times probability 2 to the x2, times probability 3 to the x3. Well, again, plugging in my values, so I have 6's in, so I'm doing 6, choose 2, 1, 3. Probability 1 was 2/9, and I'm raising that to the x1, so to the second power, times probability 2 was 1/6, raising that to the first power, times probability 3, or 11/18, raised to the x3, or third power. So now all I'm left to do is to calculate this. So this is equal to 6 factorial divided by 2 factorial times 1 factorial times 3 factorial. And then I multiply times 2/9 squared times 1/6 times 11/18. And when I do this, this is at a point that I could plug it into a calculator pretty easily and have 0.1127 as my probability that that was the way the airplanes coming in distributed.